So now we can talk about why won't work well in many real-world problems, or not even real-world problem in many games. So the first problem is that reinforce has high variance. If we look at the right figures here, so in the upper figure, right? If we have a trajectory samples like this, so this gonna represent this something look like a Gaussian here is the probability of our trajectory. The x-axis is the trajectory, and this blue line here are the value of the reward of this trajectory. Okay, and if we do a one-step update, then the Gaussian is going to look like this. Because this reward here has negative value, had a big negative value, so it will get the probability of this point to a really low value, really small value, which means the dashed line here, you can say it's near zero. And the mean of the probability will be updated to something near these two positive values. Okay, now if we add a constant to the rewards, which literally just don't change anything of the meaning of the rewards. Okay, because we add an constant to all of them, then the relative difference of these rewards are the same, which means they still represent the same thing. But to the reinforced algorithm, it does not look like the same thing, okay? Because then both of them will have a positive value. So an update of the parameter will result in a small movement, small changes here, because they are all positive values. Okay, even worse, if you get if you have at some point you have a zero reward here, then this sample data point doesn't matter to the policy gradient update because it affects nothing. Okay, it's a zero. The gradient is zero out. So this is the high variance problem of the reinforced algorithm. So there are two ways to reduce the variance. The first one is to exploit the causality. So the causality here means that it's a different meanings of the causality that you often see in academic papers. So in this case, it means that the actions after time step t will only affect the rewards after time step t, which is it's quite straightforward because the arrow of time only have one direction, right? So our action can only affect something after that time step, not the history. Okay, this is simply just the truth. So we can subtract those rewards before time step t because they are not relevant to the gradient. Okay, so this is the first one. The second one is to add a baseline. A baseline is just a value that adds to the reward. So if you remember, our reward looks something like this, and a baseline is to add a constant, or maybe it's not a constant; it's some kind of function here. But it can be mathematical proven that if you add a baseline here, the expectation will not change. It's still a valid estimate of our gradient, but the variance will change. Okay, it won't change the expectation, but it changes the variance. And after going into some math, we can even derive the optimal baseline value. And I'll say that in the most use case of a baseline is to learn a value function, is to use a value function, a state value function as a baseline. So I won't go into too much detail here. You can go to the link to to learn more about this topic. But there's another problem. The second problem is that reinforce is an on-policy algorithm. This is inefficient. So on-policy means that it has to discard all the previously collected data after each update. So if you look at the expectation here, the expectation is over the trajectory of the current parameter set theta. If after one update, then this expectation will be wrong. If after one update, we get a new policy, let's call it theta prime. And if we use the data collected by a previous policy, say theta, then the expectation, then the gradient that propagates into the new parameters will be wrong, which means that on-policy algorithm has to discard all the previously collected data after each update. Okay, and if you imagine a neural network policy that learns in this way, it's gonna hard to get it work, because we know that neural networks needs a lot of sample to learn, and typically a batch size will need something like 128 at least. And people have implemented this kind of on-policy algorithm successfully with parallel distributed RL, which means that you have multiple actors. You have a policy that works, that copies itself, like say 64. So if you have 64 actors, then you have multiple servers collecting data for you. Then for one batch update, the data will be enough. But it's inefficient, and it's also a bit costly. So this is the problems with reinforced algorithm. So for further reading, there's something like you can turn the reinforced algorithm into an off-policy version using importance sampling. Importance sampling is a trick that people use to estimate something over one distribution, but you only have access to another distribution, which is just the case we talked about here. You only have data of the previous. You have a bunch of data of previous policies, but now you want to update a new distribution. You want to evaluate the objective, the gradient of the new parameters, which are actually a new distribution. So we can do it with importance sampling and turn it to an off-policy version. Then off-policy means that you can update your policy parameters with data that come from a bunch of different things. Maybe come from human demonstrations, maybe come from other policies, maybe come from a behavioral policy that explore the world randomly. Okay, this is a off-policy version. And there's actor-corrected algorithms, which learn a Q function and use it to estimate the objective for updating the policy. Oh, I will probably cover actor-corrected in more details in the future, because it's also a big field in reinforcement learning. And the most successful algorithm, the state-of-the-art RL algorithms nowadays, they are basically all actor-corrected style algorithms, in which we have two neural networks. One is to learn a Q function, another one is to represent the policy. And we use the creative, which is the function, to update the policy. Okay, so there's a simple introduction in the reinforcement learning, an introduction book, the chapter 13.5 here. If you have the book, I have an electronic copy. I can send it to you later. And there's a link to the first off-policy actor-corrected algorithm. And note that the first actor-corrected algorithm is also on-policy algorithm. Okay. And there are other there are more advanced topics using maximum entropy as a regularizer of the objective, or self-actor-critic, which is also termed probabilistic inference RL. And there are also works that try to improve the gradient itself, which is called natural policy gradient. And the intuition is that some parameters change the probabilities a lot more than others. And using natural gradient converges a lot faster. So I don't understand this topic quite well, but you can also check out the paper and the YouTube video from UC Berkeley. And the other two popular algorithms based on policy gradient is called trust region of policy optimization and proximal policy optimization. They simply apply the idea of constraining the gradient within some scope using a probability measure called KL divergence. And it also applied the importance sampling trick to make it off policy. And there are also deterministic policy gradient algorithms, DPG, deep DPG, and distributional DPG. Okay, so these are all advanced grading topics maybe you will be interested in. I'll cover some of them in the future, I think. So today, the talk include a recap of the reinforcement learning paradigm and the DQN we talked about last time. And we talked about why Q-learning style method isn't good enough for continuous action space, because it needs an extra optimization step. And you want to optimize, if you learn a Q function with a neural network and you want to optimize it, then it's not going to be good. Okay. So, and then we talk about what is policy gradient, introduce some basic concepts, and we derived the word first policy gradient algorithm called reinforce. And then we talk a little bit about calculating the gradient with PyTorch. And after that, we talk about why reinforce won't work well, because it has high variance and it's inefficient due to the on policy setting. And I give you some further reading topics at the end. Okay, so thank you. This is today's talk.